Okay, so here we have a multiple vane problem, and it asks us to find a series of different things throughout the problem, and the first of which is the power delivered to the vane series by the jet. Now, when you are taking an exam or doing homework or anything like that, you'll have your equation sheet with you, and if you look on there, there will be an equation for power, which is power equals gamma times the discharge Q times the velocity in absolute form squared over 2g minus v out absolute squared over 2g. And in this problem, we're given v1 absolute as well as v2 absolute, and the discharge is given in the problem statement to be 4 CFS. So we know everything that we need to know in this problem, and we can calculate the power. So we'll do that as 62.4 for the specific weight of water, and then we have in the problem statement given that the discharge is 4 CFS. The velocity coming in absolute is 100 feet per second, and that's squared over 2g. We have minus the outgoing velocity absolute, which is 60 in this problem, as well, or again, over 2g. And this just gives you a number which ends up being 24,800 foot-pounds per second. And that's part A completed. Now for part B, we're asked to find the force exerted on the vane series by the water. Now, again, on your equation sheet, all that you have to do is look, and it'll say this portion right here, and then it'll also say equals fx over u, or actually it's fx times u. And so we're looking for this force right here. So we just have the force in the x direction is equal to the power over u, which is 24,800 over 30, because u in this problem is given as 30 right there. And that ends up being 827 pounds. And that's the answer for part B. And for part C, we're asked to find the magnitude of the relative velocity. This, we're going to have to start using vector triangles, which are very important for this part of the course. You first have to know how to draw the triangle and where to put all the numbers, and make sure you label all the parts of the triangle correctly given the numbers in the problem. And you also have to know how to use either the cosine or the law of cosines or the law of sines. Either one works, but sometimes it's more convenient to use one over the other. So we're asked to find the relative velocity. So to do that, I'm going to draw the vector triangle here. So we have this right here. We'll say this arrow is v1 absolute. Then we have u, which is just in the positive x direction, straight right, and then the line that connects these two is v1 relative. This is a poorly drawn triangle, but you understand the concept. So we know v1 absolute, we know u. This angle here is beta 1, and then that angle there is theta 1, otherwise known as the vane angle, incoming vane angle. So we know, and we also know beta 1, so we know 3 of these things, and that's all we need to use the law of cosines. So to do that, we have the velocity, the relative velocity squared. This is using the law of cosines. So we have this side here squared, which is equal to the other sides squared added together. So it would be this side up here squared plus this side right here squared. And then that is minus 2 times those sides again, times the cosine of the angle opposite this V relative side, which in this case is beta 1. And we can plug these values in. U is 30. V1 absolute is 100. Minus 2 times 30 times 100 times the cosine of the angle, which is given in the problem as 25 degrees. And we have V1 relative is equal to all of this. And if we just solve for V relative, it's the only unknown we have, we get the value to be 73.9 degrees. Or, 73.9 feet per second. And if you'll recall, the relative velocity is the same for incoming and outgoing. The magnitude is the same, but the direction is not. So we know here that the relative velocity is 73.9 feet per second. So I'm going to redraw this triangle. So this was 100, this is 30, this is 73.9. This angle here is theta 1, and this is 25 degrees. And that's for the incoming, that's for the top of this vane. Then drawing the same triangle, or another vector triangle for the bottom, we will have the V2 absolute. Then we have U here, and then the line that connects those is their relative velocity. And this, in this case, this angle will be theta 2, and this angle here will be beta 2. Now we so the magnitude of V2 relative is the same as the magnitude for V1 relative. It's just the angles are different. So if we redraw this triangle, we have 73.9. We have the outgoing given in the problem as 60 feet per second, and then we have 30 for the value of U. This angle is again still beta 2, and this angle is still theta 2. Those are our two unknowns for the second part. So for this next part, it asks us to find both of the vane angles, which are again here theta 1 and theta 2. So to do that, we can use the law of sines. And if that's on your equation sheet, you just have to know how to apply that to these problems. If we'll think about this first example right here, this angle here, right here, is theta 1, and if we think about the geometry, the angle on the other side of this line is 180 degrees minus theta 1. So the law of sines says that the sine of the angle, which we're going to say is sine of 180 minus theta 1, which is this angle here, over the opposite side of that is equal to the sine of another angle, which we're going to use a known angle inside combination. So we're going to use the 25, which is right here, over 73.9, and we can solve for theta 1, which ends up being 34.9 degrees. It's more in this first example, we know all three sides and one of the angles, and in the second example, we know all three sides and no angles. So for that, we have to use the law of cosines again. So we have, again, if you don't understand the law of cosines, I'm not very good at explaining it, but if you just look up any video on YouTube or anything like that, there will be someone who can explain it a heck of a lot better than I can. So this is applying the law of cosines again. Just something you need to know how to apply here. And we'll get that the only unknown in this problem, in this equation here, is theta 2. So if we solve all the algebra for theta 2, we get a value of 51.5 degrees. And that's the answer to this next part of our problem. And finally, we are asked to find the angle of the outgoing jet, which is beta 2, which is here. We can do the same thing and say that since the angle here is beta 2, we can say that this angle here is 180 minus beta 2. And again, we can use either the law of sines or the law of cosines. We'll use the law of sines here just to make it more, just to do the same as the last part. So we have sine of 180 minus beta 2 over 73.9, which is equal to sine of 51.5 degrees over 60, and we can solve that equation for the value for beta 2, and that ends up being 74.6 degrees. And that's pretty much all that you could be asked to solve for in a multiple Vane problem. You just need to know how to find all the different parameters for each of the triangles, beta 1, beta 2, theta 1, theta 2, the absolute velocities, or the relative velocity. So yeah, that's pretty much it as far as the Vane problems go. Hopefully this helps.